In 1965, humanity's reach was limited to the inner solar system. Beyond Mars lay a massive, unmapped void, and the true nature of the outer gas giants remained a mystery to the scientists of the era. That year, a NASA engineer discovered a rare mathematical opportunity. Jupiter, Saturn, Uranus, and Neptune were slowly rotating into a specific geometric alignment that wouldn't repeat for another 175 years. This alignment made a gravity assist possible. By flying close to a planet's gravity well, a probe could steal a fraction of its orbital energy to gain speed. This allowed a single craft to leapfrog from one world to the next with almost no fuel. This discovery created a ticking clock for NASA. They had a single decade to design and launch humanity's first grand tour before the planets shifted out of position, closing the window on the outer solar system until the 22nd century. To reach the outer planets, engineers had to solve a power crisis. Past the orbit of Mars, solar radiation is too thin to provide energy. Any probe sent into that darkness would find traditional solar panels to be useless that weight. The solution was the radioisotope thermoelectric generator. These devices don't rely on the sun. Instead, they generate electricity from the heat released by the natural radioactive decay of plutonium. With their nuclear power sources installed, Voyager 2 and Voyager 1 were launched from the Kennedy Space Center in the late summer of 1977, beginning their long-distance sprint toward the giants. As these machines were prepped for flight, the team realized they were building objects that would likely outlast the civilization that created them. Because the probes were on a one-way trip out of the solar system, NASA decided to equip them with a message, a curated record of Earth for anyone who might find them in the deep future. The scientific returns were immediate. Voyager 1 reached Jupiter in 1979, capturing high-resolution time-lapses of the Jovian atmosphere and discovering a faint, previously invisible ring system. Then came a discovery that changed our understanding of the solar system: active volcanic eruptions on Jupiter's moon, Io. It was the first time humans had seen active volcanism on a world other than Earth. After their encounter with Saturn, the probe's paths diverged. While Voyager 2 continued toward Uranus and Neptune, Voyager 1 used a gravity assist to bank sharply upward. It was now leaving the ecliptic plane, the flat disk where all the planets reside. In 1990, Voyager 1 turned its cameras back toward home to take the pale blue dot photo before shutting them down forever to save power. The probe was now essentially blind, drifting into darkness at the edge of the sun's influence. The planetary mission was over, but a new challenge remained. Voyager 1 was now flying toward the heliopause, the invisible boundary where the sun's solar wind finally loses its battle against the radiation of interstellar space. For over 2 decades, Voyager 1 traveled in silence toward that boundary. It was a journey into a region of space no human instrument had ever sampled directly. The goal was to find the heliopause. This is the diffusion region where the sun's protective bubble, the heliosphere, crashes into the harsh incoming flow of interstellar radiation. In 2012, a massive solar eruption provided the data NASA needed. The eruption caused electrons around the spacecraft to vibrate, allowing the probe's plasma wave instruments to measure the density of the surrounding space. Inside the sun's bubble, electron density is low because the solar wind is sparse. This chart shows the low-density readings Voyager transmitted for years. But then the data changed. The instruments detected a massive density spike. It was the dense plasma of the interstellar medium. NASA spent months verifying the numbers, but the conclusion was clear. On August 25, 2012, a human-made object officially left the solar system and entered interstellar space. While the scientific instruments tracked the environment, the probe also carried a more complex cargo. Building on the simple engraved plaques of the Pioneer missions, the Voyager team created a significantly more detailed archive of our civilization. This is the Voyager Golden Record, a 12-inch gold-plated disc containing sounds, greetings, and images from Earth. The etched diagrams on the cover explain how to play it, but rely on non-linguistic logic that would be a significant challenge for any intelligence to decipher. Engineering this record also meant working around 1970s hardware. Voyager's computers only had 69 kilobytes of memory, not even enough space to store a single modern digital photo. To bypass this, NASA used an analog workaround. They projected photos onto a screen, filmed them with a TV camera, and converted those video signals into audio waveforms. The images were literally etched into the grooves of the disk as sound. This makes the golden record a cosmic intelligence test. For an alien finder to actually see the images, they would have to recognize the patterns in the audio and reverse engineer those vibrations back into visual light. Once decoded, the record reveals a portrait of our planet, mathematical definitions, the structure of our DNA, and the sounds of our wind, rain, and machines. The images showcase the scale of human engineering, including massive structures like the Great Wall of China. These curated scenes, including the Taj Mahal, present a specific version of our world. The committee deliberately excluded any images of war or conflict, choosing instead to present an idealized, peaceful humanity to the stars. This mission is approaching its final deadline. By 2025, Voyager's power supply will likely be too low to run its instruments, and the probe will finally go silent, ending all communication with Earth. Even as a frozen, silent piece of metal, Voyager 1 will endure for billions of years. It remains a physical record of our species, a sign that on a small blue planet, life once looked at the stars and reached out into the dark.